Good afternoon, everyone, and thank you for attending. So my work here at Stress focuses on battery testing and analysis, along with computational fluid dynamics and thermal analysis of both battery systems and various other systems that we encounter across our service line. My background is in mechanical engineering, and prior to joining Stress, I worked at NASA Johnson Space Center, certifying lithium-ion battery systems for flight hardware. So as I'm sure everyone is aware, lithium-ion batteries are nearly ubiquitous in our everyday lives, whether it's from cell phones and tablets to laptops to electric vehicles, they surround us. And over time, as demand increases for longer lasting and lower cost batteries, the need for detailed battery engineering to ensure that thermal safety of the battery is maintained becomes more important. As these batteries are susceptible to a phenomenon known as thermal runaway. Now, while the mechanisms that lead to thermal runaway are fairly well understood at a fundamental electrochemistry level, this behavior manifests itself very differently with different cell architectures, battery pack designs, and the applications that they're used in. So today's talk is going to focus on an overview of the thermal hazards associated with lithium-ion batteries and the various methods used to mitigate their effects. I'll start with the basics of how batteries function and an explanation of thermal runaway. And I'll also show some examples of incidents involving battery systems, go over some ways we can improve thermal safety of battery systems, and then some examples of some of the work we're doing at Stress. So just to start, the first question that comes to mind is, what is a battery? In common English, battery is an energy storage system, but in the context of electrical batteries, it is comprised of one or more electrochemical cells. And these cells convert chemical energy to electrical energy, or in the case of rechargeable batteries, the other way around as well. They do this through reduction oxidation reactions, where the positive ion and the electrons separate and then recombine on the opposite electrode. And as I mentioned, these can be non-rechargeable or primary cells, where you can only go in the discharge direction, converting chemical to electrical, or we can design rechargeable batteries or secondary cells that can operate in both directions. Now, one of the first electrical batteries that was developed was the voltaic pile in 1799. This was constructed by stacking plates of zinc and copper along with an electrolyte material. And it was constructed in such a manner where, due to the oxidation reduction reactions that were occurring, a continuous electrical current could be generated. This was non-rechargeable. Since then, we've come a long way, and some of the common battery types that you see today of the non-rechargeable variety are alkaline cells, zinc carbon, lithium metal, to name a few. And then rechargeable types, we got lead acid, nickel metal hydride, and then lithium-ion polymer. Now, each of these types have their own advantages and disadvantages. Today, we're going to focus on discussing lithium-ion batteries, mainly because in today's market, lithium-ion comprises the biggest portion of battery chemistries. And this is only increasing with time. The main reason that this is the case has to do with volumetric and gravimetric energy densities. So this plot shows different battery types compared based on their density, starting from lead acid, moving all the way up through NiCad, nickel metal hydride, lithium-ion, and lithium-ion polymer. And then we keep going up and up towards new technologies that are still being developed today. And what we see is that lithium-ion, when you compare it to the historically common rechargeable battery type of nickel metal hydride, it's really got a much higher volumetric and gravimetric energy density. So, as we want smaller phones or electric vehicles that can have more range, increased energy density is very important because weight and volume are extremely important for these applications. Now, lithium-ion batteries do cost more than nickel metal hydride or lead acid, for example, but in these applications, the cost is worth it. The applications not so much, and that's why you still see lead acid being used today in automotive starter batteries, and nickel metal hydride still used, for standard rechargeable AA replacement cells, mostly because of cost. Now, one of the great things that lithium-ion batteries have brought us or enabled is the proliferation of portable electronics. It just so happens that when the lithium-ion battery was developed commercially in the 1990s, microprocessors and memory systems started to shrink as well. And so that really enabled cell phones as we know them today, and laptops, and eventually electric vehicles. It used to be that electric vehicles were kind of this niche idea that wasn't really competitive with internal combustion engine vehicles, predominantly because of the cost and the low range. As advancements on the consumer electronics side have pushed the costs down for lithium-ion systems, EV market starts to pick that up and drive the cost down even more, because as you have a higher production volume, you can scale your manufacturing processes up and drive the cost per kilowatt hour down. And as a knock-on effect of that, energy storage systems like Tesla Powerwall or grid-level storage systems have started to use lithium-ion more and more because the cost advantage is starting to become more real. So while there are still lots of technical and economic challenges associated with this technology, the demand has continued to grow, regardless of external market forces like the cost of oil and things of that nature. And the majority of this growth is driven by passenger electric vehicles. So diving in more into the fundamentals of how they function, we really have to dive deep into the sub-cell level, into what's called the cell sandwich. So this is really a schematic that breaks down the individual internal components of a lithium-ion battery in order to understand better what's actually occurring internally. So these various components all act in unison to enable the reduction and oxidation reactions that are occurring. Starting from the left or from the right, the cathode is a lithium metal oxide. So it contains lithium along with some sort of transition metal and oxygen. Given enough current, this can actually, the lithium and the electrons can separate, and the lithium is permitted to travel across from the cathode side to the anode side via the electrolyte, which conducts the lithium ions, and through the separator, which conducts lithium ions but does not conduct electrons. This forces the electrons to move through the load or the charger, depending on which direction you're going, and rejoin with the lithium ions on the opposite side. The current collectors are there to enable electrical connectivity in the cell. And in reality, looking at the micro scale of the anode and cathode, they really consist of the active material which stores the lithium ions and the electrons, along with a binder and some additives to really fine-tune the material to perform per the spec that's desired for the application, whether that's higher energy storage or higher power delivery or lower cost. So diving into a more practical standpoint, how do we go from that cell sandwich level up to the cells that we're familiar with in our everyday lives? So there's different form factors that are manufactured, each with their own advantages and disadvantages. The first type is the cylindrical form factor. So these are formed by taking those cell sandwiches, different layers of anode cathode separator, and rolling them into a jelly roll and installing them inside of a metal can with the current collectors welded to the bottom for the negative and to the top for the positive. These can take many forms, whether they are the common AA type that you see every day to what's called an 18650 size, which is used commonly in electric vehicles. And various custom sizes can be made. But really the advantage to this style is originally it was started for for nickel metal hydride replacement batteries, so AA's to fit in the same receptacles that they're already being used for. And then they were scaled up for higher power applications. Now they're commonly used in Tesla electric vehicles because this technology has been around for so long, it's very commoditized. So you can scale up the manufacturing process to the hundreds of thousands of vehicles per year that Tesla was targeting. It's important to note that a cell is just one electrochemical unit, and a battery is comprised of one or more of these cells. Normally you wouldn't call this a battery, you would call the entire module a battery, but that terminology often gets switched around. So they can be grouped into modules and then into packs, and the electrical configuration that's used will depend on the application. You can wire them in parallel or in series to increase voltage and capacity as needed. Some other form factors are the prismatic style, which are constructed in a similar manner as the cylindrical, just in a different external casing. And then pouch style, which is quite different. This is formed by layering the cell sandwiches and joining them together to the negative and positive lead. And this is what's commonly used in cell phones and laptops today. And like I mentioned, the form factor is really driven by the application. Depends on your tolerance for weight and size, cost, and then also if you need an active cooling system, there's trade-offs between the different sizes, different form factors on how to cool them. So really quickly, diving into the different cathode materials, there's several that have been developed over time. The most common are underlined here. Over time, as we get better and better at materials selection and manufacturing, the energy density goes up for all of these materials. But you can see, comparable to lead acid and nickel metal hydride, the majority of the chemistries available today have a significantly higher energy density. Now, with all these different chemistries, there's always a trade-off between energy, power, and then safety, which is the focus of this talk, along with calendar life and cost. So while one chemistry might be safer, it's probably not going to have as much specific energy. So real quick, diving into some other concerns with lithium-ion batteries. Fast charging is all the rage right now as electric vehicles compete with internal combustion engine vehicles. Along with cell phones, the desire to charge up your battery as quickly as possible is becoming more and more prevalent. But this also leads to increased capacity fade. In addition to that, temperature of the battery can greatly affect its performance. And this is really when we start getting into the thermal performance and the concern of thermal runaway, where high temperatures can lead to the series of reactions that releases a lot of heat and can lead to fire. And then, of course, smaller and lighter cells are always in high demand. So degradation, this focuses on how many cycles can we get out of a battery before it starts to have irreversible loss in the energy stored. There's targets that are established for this for consumer electronics and automotive. And so you have to tune the materials to allow for that cycle life. In the same manner, there's calendar life, which is really just the amount of time the battery can sit on the shelf. Self-discharge has a lot to do with this, and then also the number of cycles expected over a year. And there's several different mechanisms internally that you could spend a whole other talk going over that drive this irreversible capacity loss in batteries. And some of these are tightly coupled with the thermal behavior as well. Next, we're going to talk a little bit about cost. As I mentioned before, as we increase the production volume of lithium-ion batteries, the costs come down. And it's kind of a positive feedback loop, where as the costs come down, the demand goes up as well. So this really is driving the proliferation of these batteries in all different sectors. One thing that is of concern, though, is as the desire for cheaper and cheaper batteries increases, not everyone is approaching this the same way. Some manufacturers are approaching this by using lower quality materials or decreasing the size of the enclosures used for these batteries, which can lead to potential safety concerns. Another issue to consider is the environment and the resources required to build these batteries. There's a significant climate change and ecological impacts due to the mining of these raw materials, along with the concern of resource depletion and issues with recycling that really prevent batteries from being a complete replacement for internal combustion engines, at least for the near future. And that also drives into the fact that emissions truly aren't zero for electric vehicles. It really depends on the manufacturing process and the source of the energy used to charge the electric vehicle battery. So there are some alternatives that are on the horizon. Lithium sulfur, lithium air, and solid state electrolytes are all in development right now. And the researchers that are developing these technologies, their goal is to alleviate a lot of the problems that I just outlined, in addition to alleviating the thermal safety challenge that we're going to go into detail here in a minute. So as I alluded to it earlier, lithium-ion batteries suffer from a critical disadvantage. And as in anything in life, a perfect battery does not exist. People are working on it, but right now it doesn't. And right now, lithium-ion provides us with very high energy density, very high power density, good calendar and cycle life, and a relatively low cost that's decreasing with time. They're not inherently safe. Thermal runaway can start through a various number of abuse mechanisms, whether it's external or internal short circuit, very high or very low temperatures, improper charging or discharging, and then mechanical abuse as well. All of these can lead to an increase in the internal heat inside the cell, which actually triggers a series of decomposition reactions in the different components inside the cell, particularly the highly flammable electrolyte. These reactions are exothermic, so they continue to increase the temperature of the battery, which then feeds subsequent exothermic reactions, leading to a positive feedback loop that, if unmitigated, can lead to fire or explosion. But that's not to worry. There are several protection mechanisms that battery engineers use to mitigate these effects. One is battery thermal management, so monitoring temperatures, voltages, currents in the battery, both at the cell level and the circuit level, to monitor and make sure that these conditions that generate thermal runaway aren't being reached. That doesn't always work, but it works most of the time. And really what's key is before using a battery and starting to manufacture a battery system, you need to do sufficient testing and make sure that system is certified against the various standards in place to make sure that it's going to safely operate. As mentioned, these batteries experience thermal runaway when they're operated outside of their design conditions. This can be due to any number of those abuse mechanisms that I highlighted, and they can lead to fire or an explosion. And the onset and severity of this reaction is dependent on a lot of factors. These are just a few. But state of charge is very important. How charged up is that battery? The method used to initiate thermal runaway, whether it's external short or external heating, the active material used, the chemistry in the cathode in particular, the electrical configuration, the form factor, integrated safety features, and the method used for thermal management. Those are all very important. And something that's going to be a key theme in the presentation moving forward is that single cell thermal runaway, while it's a problem, the worst scenario is when that single cell emits a lot of heat and causes a propagation of thermal runaway in a multi-cell battery. So in order to make sure that the battery system functions even under abuse conditions, cell manufacturers use testing to certify their designs. And then there are several transportation and packaging regulations in place, and then device level standards and testing for various industries. Pretty much any industry that uses battery systems has some sort of standard that discusses the steps that must be taken to ensure safe operation. So what is thermal runaway and what causes it? So I mentioned that there is this feedback loop between side reactions and increased cell temperature that really drives the runaway behavior. This happens throughout the cell in the different components. Each has its own decomposition reaction that has a characteristic heat output and onset temperature range. In general, the accepted pathway is as follows. The protective layer, there's a layer that forms between the active material and the electrolyte called the SEI. That starts to decompose at a fairly low temperature. And then the heat from that reaction then feeds into the electrolyte decomposition and flashing. The electrolyte is a hydrocarbon-based material. That flashing, if unabated, will continue to increase the pressure inside the cell and eventually rupture the cell itself. This is actually intended in some cases to reduce the risk of explosion. And then at an even higher temperature, the separator starts to melt and you get an internal short circuit. That dumps a lot of electrical energy into the cell in the form of joule heating, which can then cause the cathode to decompose, which in many cases releases its own oxygen, which can prevent suffocating style fire suppressants from working properly. So the abuse mechanism can either start at step one and move through the different side reactions, or in the case of like an internal short, can actually skip to step 4, which provides the heat required to go back to step 1 and move through the sequence. So in general, this is the mechanism of thermal runaway. And like I mentioned before, there's a lot of variation to this depending on the architecture of the cell and the abuse mechanism. So why is it important? Why are we concerned with battery safety if we can just use cells and make sure that they're always used in their operating conditions? Well, history has shown us that even if we design a perfect battery system and operate it in the way it's intended, bad things can still happen. There have been numerous safety incidents that have led to personal injuries and significant monetary losses due to recalls. And this is just a selection of a few that I'm going to go over. In some cases, the batteries can be the source of a more significant incident. So, sometimes a regular battery that's used for a cell phone or a laptop can start a fire, which then propagates to the structure of a vehicle that you're in or an electrical component that you're using. And so understanding and mitigating the risk associated with these applications is really important, and these case studies teach us a lot about that. So first, starting with the Dell laptop battery fires, the point of origin for these fires was actually manufacturing defects in the Sony cells. The separators were too thin, they're out of spec, along with the cylindrical cans. And as with any manufacturing process, there's always a little bit of variance and in some cases metal contamination. And that can lead to a significant recall, as it did in this case, and significant monetary losses as well. Manufacturing defects are very difficult to isolate, and it really comes down to how rigorous is the manufacturer in maintaining a clean room environment and how much screening do they do before sending these cells out to ensure that they're safe for use. The Boeing 787 battery fires was another very publicized incident. Again, there was a defect in the cells, but really what caused the fire was thermal runaway propagation from cell to cell. And so the finding coming out of this is really what started a lot of the recent work that we've been doing to study propagation and how to mitigate it. Electric vehicle fires are fairly common, but they're actually less common than regular internal combustion engine fires. But the key thing with electric vehicle fires is that the firefighting best practices are somewhat different than regular vehicle fires, and so additional training is needed for the firefighting personnel. There are high voltage lines that have to be disconnected, and then, like I mentioned before, the chemical fire suppression is often insufficient for these fires. Really, the firefighting method is to significantly cool the battery by pouring water on it. In many cases, it can take several hours to actually fully extinguish the fire because the reaction inside the cells is propagated through the entire module fairly quickly. The other concern is a term called stranded energy, which has to do with if you fight the fire on one end of the battery module, the rest of the battery module might still have electrical charge. And so you have to figure out how to safely de-energize that system before transporting, because as you pull it onto the tow truck, you can actually reignite the cells and cause significantly more damage than the original fire. Just like the electric vehicle fires, there have been some fires in the maritime world. So one such fire was actually caused, or the presumptive cause was several phones and other portable equipment were being charged overnight in one location. Some kind of fault occurred in those systems, and the fire propagated to the structure of the boat. And so the US Coast Guard issued an advisement against unsupervised lithium-ion battery charging. But that's not to say that people still do it. So this is an example of how not only is it important for engineers that are using batteries in their jobs to understand the mechanisms, but also important for the common person, the everyday person, to understand the risks involved in these batteries and take measures to mitigate that. Another example is actually a hybrid vessel that has an energy storage system on board that can provide propulsion. This battery had a fault and started a small fire. During firefighting, there was actually quite a bit of gases that were released from the batteries, which were collected in the battery room and subsequently caused an explosion. So coming out of this, the Maritime Authority recommended a reassessment of the risk matrix for these hybrid vessels and updated the procedures for firefighting to prevent that. Just some other incidents that are of note. A cargo plane caught fire and crash landed with a shipment of 81,000 batteries. The halon system on board was insufficient for these batteries, again, because the oxygen inside the cathode can fuel the fire. And hoverboard battery fires were fairly common due to poor manufacturing procedures. And these were recalled and caused lots of damage. And then the Samsung Galaxy Note 7 fires were also fairly common. And again, due to an engineering mistake, really, due to the fitment inside the phone itself. It actually caused an internal short circuit. The recalls cost Samsung a lot of money, and they were obviously in a hurry to get new batteries fitted and new phones sent out to customers. And there's actually a second round of recalls for the new battery because they were rushed. There were actually some welding defects. So it just goes to show that even if you take the right precautions, if you are rushing a product, that can lead to bad consequences as well. So mainly because of the Boeing fires and the UPS cargo plane crash landing, a lot of the battery transportation regulations are kind of in flux right now. They were updated continuously over the past several years by the numerous organizations that govern this, and so they're constantly evolving. And a lot of the work that we've been doing has been focused on helping these organizations develop the test standards that are being used to ensure that these batteries are safe before flight. So in addition to that, outside of transport, there's several different governing bodies that have put out standards for batteries in all kinds of applications. This A lot of these tests are done on anything that's UL listed in the United States, and then the EU handles their certification process a bit differently. But again, the industry. Sorry, my mic cut out for a second. The industries that that these batteries are used in really are who's governing the different policies that are being used to test these battery systems. So what can we do to increase battery safety? We've already talked about how regulations help with that, but as a battery designer or user, what can you do? One is to limit the amount of active material present, which reduces capacity. This is often undesirable because the whole benefit of using lithium-ion is the increased energy density, so you're kind of taking a step back there. You can include safety mechanisms. These mechanisms work pretty well, but they do add weight and increase volume and also increase the cost of each cell. But I'm going to cover some of the different types available. The first is what's called a current interrupt device. This is a mechanical fuse similar to the top of a jar that disconnects current when the electrolyte flashes. And it generally helps multi-cell modules because it prevents a short circuited cell from becoming a module level short circuit. The next safety device is a PTC, or a positive temperature coefficient device. This is a polymer type device that acts as a thermal fuse. It typically activates before the CID, and it prevents off-nominal currents in the pack from heating the cell in particular up too quickly. Another one is the relief vent, which will open. It's irreversible, but it opens when the pressure inside the battery exceeds a threshold that is deemed unsafe, and it prevents explosion. And then electronic protection circuits are required in almost any battery that's used today. And they monitor the voltages and the currents at the battery level and have solid state fuses that can open up if anything is detected as off nominal. So obviously one would expect that these safety devices are included in every single battery that's manufactured, but that's often not the case. It just depends on the application and the relative tolerance for risk that the application has. You can also include thicker cans and separators, higher quality materials if you really want a robust cell. And you can also increase spacing between cells to prevent propagation risk. And then battery health monitoring systems can monitor the health of the battery in real time, which is beneficial. And then lastly, pre-installation cell screening is very important, but not always done depending on the volume of cells that we're talking about for an application. For example, for space applications, each cell is screened using CT technology because they're only going to send up a couple batteries, and they want to make sure that whatever they send is the best that they can send. So for every one battery that goes up, these guys are testing hundreds, if not thousands, of batteries on the ground beforehand. So as always, we want cheaper, lighter, and smaller cells and more capacity. And so, as I mentioned before, these safety devices kind of hinder that that desire. And so they're not always practical to use depending on the application. They don't protect against manufacturing defects as well, and there's variability in the design of these devices that can cause them to function in some cases, but not in others. It's also difficult to protect against external mechanical or thermal abuse. You can account for it in your risk matrix, but there's no telling what the end user is going to do with these batteries. So you can't always account for everything. Some electrochemistries are more benign than others, as I mentioned before. And so you can, if you're particularly risk averse, you can select a chemistry that has a low chance of poor thermal behavior, but usually at the expense of one of the three, capacity, life, or performance. And so at the end of the day, safety testing is really needed to understand this behavior. This is already done at the cell level prior to transportation, governed by UN. But at the component level, testing is also needed, and that's controlled by the industry standards. And then also there's testing that's required for the battery pack as it's installed inside of whatever component it's powering. So what kind of tests can we do? The different types of abuse tests are electrical, mechanical, environmental, and then miscellaneous tests. Some of these are covered under existing standards for transportation alone, and some of these are covered under the industry standards. So it really just depends on where your battery's going, which test you need to do, and they each kind of drive different types of abuse scenarios. In reality, electrical abuse is really leading to thermal abuse, as is mechanical. The mechanical causes an internal short. That internal short creates internal heating inside the battery, which then leads to all these side reactions. So at the end of the day, thermal runaway is a thermal phenomenon driven by heat, but the mechanical and electrical abuse are pathways to that internal heat. All right, so first I'm going to show an example of external short circuit. This is a lithium polymer cell, and it's subjected to an internal short. Typically, the external short is of a resistance that's less than the internal resistance of the battery, and that creates a worst case condition. This is driven by joule heating of the battery due to the high currents. And that heating leads to flashing of the electrolyte and eventual venting. And those electrolyte vapors combust due to the high temperature of the tabs of the cell, which leads to the large fire. Next is an example of a crush test. This is kind of similar to the external short, but instead we're inducing it through an internal short mechanism due to the mechanical penetration of the nut into the battery itself. But the thermal runaway mechanism is the same. Electrolyte vapors release and then combust. And another example is a nail penetration test. So this test is really trying to simulate an internal short circuit instead of an external, where there's a manufacturing defect inside the cell, and it leads to a puncture of the separator and short circuit. This is a multi-cell test with 24 cells, so we also see the effects of thermal runaway propagation. This is using a nail penetration style device, but there are actually cells that have been developed today that have built-in internal short circuit devices that melt the separator inside and are more controlled. Okay, so those are just some examples of abuse tests. Now, how do we take those tests and apply them to help develop standards and study thermal runaway propagation at a higher level? So on the next slides, I'm going to show some testing examples of work that we've done at Stress, including runaway propagation testing, containment tests, standard development tests, long-term storage, and fire resistance exposure testing. This is all done at our Waller test facility, where we have lots of equipment to characterize the cells electrically, and also have various chambers for environmental control, abuse testing, and large external fire testing, gas analysis using GC, and a lot of in-house instrumentation and data collection. So this first project is focused on assisting our client with the development of new packaging standards. The results of this test are really to understand the test methodology better and determine a suitable method for repeatable results, studying the method used to initiate thermal runaway, the location of the initiation and the protocol, and how it influences the final result. And then study different measurement locations and different pass-fail criteria. Some of the other experimental variables that were studied were the state of charge, the packaging format, and the form factor and capacity of the cells. So this is one example of a typical shipping configuration of 18650 cells. We're mimicking how these cells are typically transported before they're used to assemble a battery. And what we're doing is we're applying external heat to the center cell using a Kapton heater. And in this case, this is for a battery with a high state of charge. And so if we skip ahead, we start to see thermal runaway reactions in the trigger cell, and then it propagates out to the neighboring cells, causing a release of electrolyte and rapid explosion of the cells. Now contrast that with the same test, but with a low state of charge, and all we see is a mild thermal runaway on the initiation cell, some smoke release, but no propagation. So this kind of highlights the requirement that we're seeing for shipping of these cells, where the SOC, the state of charge, has to be less than 30% in order to ship large quantities. Now, what we did see in the testing was that in some cases, even at low SOC, you can still get thermal runaway behavior. So SOC is kind of a stopgap that helps screen cells and ensure a baseline level of safety, but it's not exhaustive. So another style of test is looking at thermal runaway containment. So let's say you need to ship batteries because let's say you're a sports team and you have a lot of radio equipment all have batteries in them, and you want to ship them charged, so you don't have to charge them when you land. Well, in order to transport a large quantity of batteries on a passenger plane, you need to prove to the governing bodies that if something were to happen with those cells, that it wouldn't cause a fire in the cabin. So this case is an aluminum construction with fire suppressant built into the walls of the case. And as you'll see here in a second, thermal runaway occurs, and then the fire suppressant material drops down and actually puts out the fire. So after the test, we see that the initiation cell went into runaway, but we did not get propagation cell to cell. So the case worked as intended. Another test example is the standards development for the SAE G27 committee. This is really looking at what happens when you get thermal runaway and you have gases escape the cells and they collect in a storage container on a cargo aircraft. What do those gases look like? What's their composition? How flammable are they? And can we develop packaging that helps mitigate the risks associated with that gas? So in this test, we're letting the gas collect, and then we're actually using a spark igniter to combust the gases and measuring the heat output and the gas composition before and after combustion. Another standards development project example is the UN lithium battery classification standards. So the intent for this one is, instead of classifying batteries in terms of their lithium metal content or state of charge, what if we tested each new battery and gave it a rating in terms of the amount of risk associated with it thermally? And so this is intended to supplement the existing safety testing that's already required for each new battery that is developed. And it would actually be extended potentially to a labeling requirement, which would require each cell is labeled based on their classification, their hazard classification. So this project was in collaboration with UL and worked with the battery classification committee. And we ran over 400 tests, various different form factors, states of charge, cell chemistries, and we performed external heat tests and external short circuit along with calendar life studies as well. So really it was quite exhaustive. Some additional areas of testing that we've done on these projects, looking at the initiation method, the heating rate, and the protocol, how it affects the thermal runaway behavior. The higher rates tend to lead to a lower vent and thermal runaway temperature and a more energetic release. And looking at different battery types as part of the previous study, looking at pouch cells versus commercial off-the-shelf battery packs, like for laptops or cameras. Studying how the enclosure and the circuitry surrounding the cells affects thermal behavior. And then again, looking at state of charge and how it affects thermal response under external short circuit and also over time. And then looking at combustion gases and studying different cell types and the constituent combustion gases. Does one cell chemistry lead to combustion gases that are less flammable or more? And then also looking at some unique industry-specific tests like fire resistance testing, which is used for the automotive industry to ensure that passengers have enough time to exit a vehicle during gasoline spill fire. So in addition to testing, there are some other topics that are pretty important to assess battery safety. Design and analysis is also very, very important. And this is something that we've worked with in the past to do battery module design and thermal safety focused modeling to ensure that battery designs are capable of handling a variety of abuse conditions. The level of testing or analysis is really variable depending on the application. So, I'm listing a few applications here that are fairly common. If you're looking at grid storage, for example, you may be less concerned with thermal safety than if you're looking at flight hardware for an aerospace application or an automotive application. So really, the test or the modeling required is really dependent on the end user application. Now, these are testing analysis prior to installation of the battery or commissioning is just one part of the battery safety picture. The other part is failure analysis, or what we call DPA, which is assessing these batteries after they failed to glean understanding of thermal behavior. And that really helps drive a lot of the testing and analysis work that we're doing. So in closing, again, as demand drives the energy density up for these batteries, the thermal safety becomes even more critical. We've shown through our extensive work here and then in industry and research and academia that as these energy densities go up, the risk associated with thermal runaway also goes up. But that being said, after incidents occur or after further understanding is reached on the research side of things, the battery community is really continually developing these safety standards to adapt to the increased energy densities and increase proliferation of the batteries. But until the next generation of rechargeable battery technology can compete with lithium-ion in terms of cost and energy density, this thermal safety concern will remain. So in that regard, extensive test programs and modeling and design work is really key to meeting the standards and meeting the requirements of the end application while minimizing risk. And with that, I'd like to thank you very much. I hope you found the presentation today to be informative.